I'd like to welcome everyone to today's e-showcase, Opportunity, How Municipal Wastewater Utilities Can Be a Part of a Comprehensive Phosphorus Management Solution. I'd also like to thank today's sponsor, Evoqua. Let's see if I can. Here we go. Thanks to our sponsor, Evoqua Water Technologies. I also have the pleasure of introducing today's presenters, Casey Whittier and Matthew Kuzma. Casey has been with Evoqua for 25 years and has worked in a number of roles ranging from field process engineer to applications engineering to his current role in product management. Our speaker, Matthew Kuzma, Vice President Astera, has more than 20 years of water and wastewater management experience ranging from large multinational corporations to venture capital-funded technology startups, including 5 years with Astera as Managing Director, Nutrient Recovery. And now I'll hand the presentation to our presenters.
All right, thanks everyone for joining. I'll be starting off the presentation, and as we get into it, Matt will talk about the fertilizer offtake towards the end of the presentation. So with that, we'll get started. Again, thanks for joining. Today we're going to be talking about a nutrient recovery technology from Astera that is able to recover nutrients from where they shouldn't be, which is the wastewater, and transform them into a high-performing, sustainable fertilizer product. So we'll give you guys an intro to that and let you know how it fits into a municipal wastewater treatment plant. So before we get started on that, I think one of the new things, a lot of you may have heard of Astera and the technology they offer for resource recovery. Something that's newer is Astera and Evoqua have partnered together to bring this technology further into the market. We feel there's a greater impact of the two companies working together. Astera will still continue to handle the process technology and fertilizer management side of it. And then Evoqua brings to the table a broad reach into the market on the sales and marketing side and expertise in project delivery for these types of systems. So with this, we think this will allow the technology to have an improved financial and environmental sustainability to the market, which should allow for increased adoption of resource recovery. It's made a lot of progress over the last 10 to 15 years, but this really should allow us to further get into the market and create that awareness. In addition to that, it allows for, with Evoqua and already our reach into phosphorus management, it allows us that missing piece, which is resource recovery. It combines well with some of our removal technologies that we already apply to phosphorus removal, like COMAG and our 40X disc filter. So with that, jump in. With this technology, again, this is really something that helps create a circular economy. It's a word you'll hear about throughout the presentation. What we're doing is we're taking a renewable resource that's already present in the wastewater, which is phosphorus, and to some extent nitrogen as well, as you'll see. And by applying the Pearl system, which we'll give details on further in the presentation, we're able to take that nutrient and turn it into a sustainable fertilizer. This then is applied in agricultural and creates a product that significantly reduces runoff back into our waterways. So you've got point source treatment that you're dealing with at the wastewater plant, but then another big part of nutrient pollution is the non-point source agricultural runoff. And as you'll see, the product that comes from the system really helps address that issue as well. This leads to positive benefits in regards to environmental impact by reducing those nutrients from getting back in the waterway, and then also in regards to addressing challenges of a growing population by addressing issues with water scarcity and then food production. So this isn't a new technology. Like I said, Astera has been around since the mid 2000s and has created quite an established installation base. There's 23 installations of the Pearl system worldwide. Most of it within North America and Europe to this point. So the agenda for today, with those intros out of the way, is number one, we're going to start with why phosphorus recovery is important. And then we'll look at what problems the nutrient recovery solution solves within a plant. Give a little background on how the Pearl system with Wasp Strip, which you'll see later, works to address these issues. And then, like I said, I'll turn it over to Matt towards the end to talk about the benefits of the crystal green fertilizer that's produced in the process. So to start with, phosphorus is an essential element for all living organisms. It's a building block of DNA. The human body is made up of approximately 2% phosphorus, mostly in teeth and bones. And finally, there is really no known substitute for phosphorus, so it really is essential to life. The challenge is the phosphorus cycle today is broken in that um, we mine it, it goes into industrial systems to produce fertilizers and other products. There's waste generated from that. These products like fertilizer, more conventional fertilizers, then go into agriculture for food production. And the challenge is, as you'll see, these products are water soluble, and as you get large rain events or storm events, a lot of this runs off back into the streams rather than where it needs to be, which is growing the crops. Along with this food that's produced, then humans create waste, as we all know, that goes to the wastewater plants. And if left untreated, that becomes a point source of pollution for phosphorus. So between the point and non-point sources of pollution, that gets back into our waterways, causing algae blooms, which we've all heard about, that can damage and destroy our ecosystems there. So as we look at the solution here, this helps the Astera nutrient recovery solution helps close that gap and start uh, reusing, treating at the plants and reusing the phosphorus that we take out there to create the crystal green fertilizer. And as you'll see, as we talk about that, the crystal green fertilizer that's produced is not water soluble and does significantly reduce runoff back into the stream. So by implementing effluent limits on plants, we can address the point source solution with technologies like I mentioned earlier, like COMAG, disfilter, and other things, biological phosphorus removal in plants. And then by recovering that resource with the Pearl system, now we're able to keep it from getting back into the streams through runoff through agriculture as more and more of that's applied. So now we'll get into what the problem we're really addressing is. So in a municipal wastewater treatment plant, like I said, we've got phosphorus coming in the wastewater, and as more waterways are getting impacted by nutrient issues, you find more and more plants are addressing the issue of point source pollution by implementing stricter and stricter phosphorus limits. As low as 0.05 in some places, milligrams per liter we've seen. But as those, so we're addressing a lot of it at the plant level. And one of the things that plants are doing to address this is adding, as they upgrade their systems, they're adding things like biological phosphorus removal in the mainstream, which is a nice cost-effective way to get that phosphorus out of the discharge. The challenge with that, as we'll see, is that in the side stream that goes to digestion, this can now lead to additional issues, maintenance issues with struvite, unwanted struvite buildup in parts of the plant where we don't want it. So before we get into it, some of the benefits we'll be looking at as you learn more about the Pearl system. Number one is it can reduce up to 70%, or it can get up to 70% recovery of the total phosphorus load to a wastewater plant. In addition to that, as you'll see in the basic ingredients of struvite, it also uses takes up ammonia. About 15 to 30% of what would be recycled back from the digester is taken up as part of the process, which reduces the aeration requirement in the main system. By taking it out as a product and avoiding struvite in the sludge cake and or chemical sludge from taking that phosphorus out by other means, you get a 10 to 20% sludge reduction possibility in the plant. Up to 90% reduction of digester struvite, which can be lower the cleaning frequency and give you more room in your digester for what it's supposed to do, which is digest biological solids. And then dewatering improvements as well by you can get a 2 to 4% improvement there, and a corresponding 10 to 15% reduction in polymer usage. So the core of the technology, as I've mentioned the Pearl a few times leading up to this. In the following slide, we have a diagram of the Pearl system. As I said, the basic the crystal green fertilizer is struvite. Its core ingredients are magnesium, ammonia, and phosphorus. Those ingredients are present in municipal wastewater plants, so that's part of why you can get unwanted struvite buildup in places like the digester and pipes. So what we're doing in general with this technology is we're taking those ingredients and making a product out of them in the Pearl system so they don't become an issue in those other places. Uh, in the Pearl system, basically we have the nutrient-rich stream that feeds the bottom of the upflow fluidized bed reactor. To that stream, we do have some additional magnesium and pH adjustment to really create a supersaturated condition in the reactor to properly form those struvite crystals we're looking for. Towards the top of the reactor, we have a recycle stream that helps maintain that fluidization rate and create the right concentrations at the bottom of the reactor to get that struvite formation. Out of the top of the reactor, you have a treated effluent that's now low in phosphorus and reduced in those ammonia concentrations as well. And then you'll see towards the bottom of the reactor, we have a harvest line. So as we continue to grow struvite and build the product, occasionally you're going to harvest some of that out into that crystal green fertilizer product. So within the family of the Pearl system, we have a number of different or several different reactor models. We have the traditional ones that Astera started with, the 500K, 2K, and 10K reactors. Those are similar to the diagram we just looked at that have a recycle stream. Something a bit newer that has come to the market is the Pearl FX system, which we'll talk a little more about in a few slides. It is really intended for some of the smaller plants out there, say 5 to 30 MGD, and it provides a reduced capital approach to putting the Pearl system in. We'll go through exactly what that design looks like as we get into this, but one of the key differences is it does not have that recycle stream. So now let's look at why and how we apply uh, the Astera technology into a wastewater plant. So to start with, we'll look at a conventional flow diagram for a wastewater plant. You've got your primary clarifiers and activated sludge system, and then on to discharge. Depending on phosphorus limits, maybe there's some tertiary treatment and things like that as well. But for what we're talking about here, we've got a conventional activated sludge plant. Off the clarifier, our waste solids go, in this case, to anaerobic digestion, onto dewatering, and then there's a recycle stream that comes back around. So one of the first ways that a lot of places look at to deal with that phosphorus issue is before they've upgraded and as they get these phosphorus limits is to add metal salts to get rid of this problem. So that does fine with getting rid of the phosphorus, but it does lead to quite a high operating cost from adding those chemicals and also the increased sludge that goes with it. If left untreated with those chemicals, you do get recycle of phosphorus and ammonia back through the plant anyways as it releases back in the digester. So that's one way to do it, but I think as you'll see as we look at it, there's better ways just from an operating budget and solids production and all that to deal with that issue. So that leads us to as plants start to implement their limits, the common one of the more common upgrades out there that we're seeing more and more of is what's called biological phosphorus removal. So as they upgrade that activated sludge system, they add an anaerobic tank in front of their aerobic zones on the activated sludge. That anaerobic tank releases phosphorus, like you see in anaerobic digestion as well. And then as it hits that aerobic tank, the bacteria, as they adapt to it, become like a sponge and they suck that phosphorus up at higher rates than what a normal system would have. So, versus about 2% in your sludge, you now can run upwards of 4% and more in your sludge that goes to the digester. So that's good, and that does a good job of getting the phosphorus out of the effluent of the plant. So we're dealing with the point source discharge there, but we've still got it in that side stream that goes to the digester. And so what happens then as it hits that anaerobic digestion, like I mentioned in the activated sludge, you get phosphorus release there. And you also are producing ammonia. And so as that goes back around, a lot of that 20 to 30% of that ends up going back around, and you still have to deal with it in the mainstream. In addition to that, like I mentioned earlier, you do have the ingredients in this to form struvite without putting the pearl system in. So this is where you start leading to issues in your recycle stream of struvite buildup where you don't want it. And you can see in the picture there is an example of struvite buildup in the pipes, which in addition to that going back around to the plant, you get maintenance issues to deal with your pipes clogging up over time. So to address that issue, this is where the Pearl system comes in. Initially, we add that on that stream after dewatering that recycles back to the plant. So it's high in phosphorus, high in ammonia. It's got the magnesium in it, so we can put the Pearl system there to deal with, to form that struvite in a controlled manner, take it out, produce a sustainable product with it, and now that's reducing that load back on the main part of the plant. Now, what that doesn't address, as I mentioned, is build up in the anaerobic digester itself. You still have those conditions there as well. So with just the Pearl system on that dewatering recycle stream, doesn't eliminate the buildup you'll get in the digester because you still have the ammonia, the phosphorus, the magnesium, all in that anaerobic digestion system. So you still have a maintenance issue potentially there with just the Pearl system alone. And that's where the second part of the system comes in, which is the Wasp Strip. And again, lots of anaerobic tanks that I'm talking about in this, but what this really allows us to do is by putting an anaerobic tank on the waste stream before it goes to the digester, you're able to take off because there's in this tank it's not held as long as we're talking hours rather than 20, 30 days of holding time. So we're releasing that phosphorus like you do in the activated sludge and able to take that stream of high phosphorus and magnesium directly to the Pearl reactor. Now it goes to the anaerobic digestion, which before it goes there does not have the ammonia. That's part of the digestion process. In the digester, we create that ammonia as we're digesting the solids, go through dewatering, and now we combine the three items where we want them, which is at the Pearl system. And so by doing that, now we're able to significantly reduce struvite production in the digester up to 90%. And so you can see in this picture with a system with Wasp Strip before and after the difference as you spin down solids on what is in the system with struvite. And so just roughly each ton of magnesium diverted around the digester results in about 10 tons less of unintentional struvite formation in the digester. So the combination of the two really allows you to both increase your recovery through the system, more fertilizer, and also greatly reduce those maintenance issues associated with unwanted struvite formation in a plant. So to summarize benefits we see by adding the Wasp Strip plus Pearl system into a plant for nutrient recovery, we're reducing the phosphorus recycle back around to the plant, reducing maintenance from unwanted struvite buildup, both in the digester and in the pipes. There's improvements in dewaterability, reduction in polymer demand, and reduction in sludge production compared to adding chemicals alone or putting the struvite out in the sludge. On the economic side, many of the operating costs of the system can be offset by the fertilizer recovery. It's a commercial product that Astera can buy back from the plant. And then from an environmental standpoint, you're getting a full cycle resource recovery. That phosphorus is coming back out, being turned into a sustainable product. And also by reducing things like ammonia recycle and phosphorus back around to the plant, you're helping with your carbon footprint as well. So that's the basics on what the Pearl system does with Wasp Strip. The other part to the system is handling the product after we harvest it from the Pearl reactor. So as you can see in the diagram here, um, following the Pearl system, we've got uh, a means of dewatering it through a screen and then a dryer, and then we have a way to classify it on site where it gets bagged or trucked off site, um, either as a commercial product or onto an Astera facility for further processing into a final end product. And you'll understand more about that as I talk about the Pearl FX. So in some cases, the plant's right out of the reactor as it goes through that product handling system produce a fertilizer ready for market. And then in other ones, as we look at the Pearl FX, we get a rough product out that's further finished at an Astera facility offsite. So with that, we'll move into the Pearl FX. And again, some of the differences. So it's still the same type of fluidized bed reactor. It's a lower capital option. As I'll show you what this system looks like, you'll see what I'm talking about. One big difference, like I mentioned earlier, is this system does not have recycle, so it's a single pass reactor. This allows for a reduction in instruments and control architecture that go with the system. And again, on the product handling side, we're still going through drying and those types of things, but we're not classifying it. There's some smaller amount of equipment required there that helps manage the costs. And finally, as you'll see, it's a modular delivery. So it's a skidded system. There's a few pieces to it. Put it on a slab, connect to it on site, and off you go. So that helps really reduce the installed costs of the system. So this is a schematic of what the system looks like. As you can see, we've got the reactor module. We've got an optional stairway module that goes with it. And then we've got a skid that contains the chem feed and the dryer feeder and hopper with the dryer on it. So basically you've got a reactor skid, um, product handling skid, and the stairway that go with it. Set those up on site, pipe pipe to them, run the electrical, and off you're going with it. As an example of what the system can get you, so looking at a 15 MGD plant and providing the system in this method, you get about a 12% can get about a 12% reduction on equipment design and construction because you're not putting all these systems together in the field. They come skidded ready to go. You're getting a significant savings on the design and construction side of it. And overall, on this example, about a 37% reduction in the overall installed price of the system. So that can make a big difference on the smaller plants where you're not making as much product from the system, but you're still able to get that out, eliminate your problems, save some chemicals, and produce a sustainable product out of the facility. So there may be other bigger cost savings potential in on other sites, but this is a typical example and something we can look at as the opportunities come. And so with that, I'm going to turn it over to Matt to talk about the benefits of the fertilizer that's produced in the system.
Yep, thanks, Casey. Yeah, so coming out of all of the Pearl systems, we have a Crystal Green as our brand name on the fertilizer side. And from a business model standpoint, essentially, Ostara will contract with each of these sites to buy the fertilizer that they produce. So the sites don't have to deal with logistics of seasonal storage, warehousing, regulatory certifications and documentation, marketing, quality control, all of those kind of things. But um, going back to the original introduction, we have to address both the point source and the non-point source challenges if we really want to protect our waterways. And this solution really allows us to address both components. Ironically, even though it's coming from what's perceived to the public as a waste stream, it actually is a higher purity fertilizer product than the fertilizers currently on the market, commodity products that you would buy today. Um, and the precipitation reaction, the crystallization in the reactor is exclusionary, so that if you look at the APFCO limits, which is the regulatory body on fertilizer for heavy metals, MAP, monoammonium phosphate, DAP, diammonium phosphate, and TSP, triple superphosphate, all have significantly higher content for the heavy metals because of the mined fertilizer production. Ironically, if you look at Europe, for example, they're using crystal green to dilute down commodity fertilizers, primarily on cadmium, because of the cadmium content on some of their products as is. So even though it comes from a wastewater plant, it is actually a higher purity product than most products on the market. Um, then if you look at the data that's been collected on the application of the fertilizer, we've looked at both groundwater and surface water impact. So this is an analysis or a trial done Auburn University several years back. And if you look at the trials here, you have MAP 100, which is 100% MAP, MAP crystal green blend, and then down at the bottom you have 100% crystal green and the control. And what this essentially is looking at is groundwater impacts of fertilizer after irrigation and rainwater events. And so you see the days across the horizontal axis, and then the cumulative orthophosphate impact on the groundwater. And what you essentially see is that MAP, as a highly water soluble product, ends up running off relatively quickly in the first, say, 20 to 30 days, and then plateaus into the groundwater, whereas increasing rates of crystal green blending, and then at the bottom, the combination of the crystal green in comparison to control, because it's not water soluble, and you see that in wastewater plants. The problem with the unintentional accumulation in pipes, etc., is that it's not water soluble. And now that becomes a benefit in the field because it doesn't run off with those irrigation and rainwater events. But essentially, crystal green application is the same as the control, meaning that not applying phosphate and applying crystal green has the same impact on the water body, which is certainly a good thing. This is a very similar study. In this particular case, it was looking at surface runoff. So this is done in the UK. Essentially, they put troughs around the outside of a small field, and then they measured phosphorus content in the runoff around the sides. And again, the same story at the bottom. You see the no phosphorus, meaning the control, as well as the crystal green essentially being flat at the bottom with no impact. And then up above, you see TSP, and then TSP plus Avail. Avail is an enhancement that's commonly used with TSP. But if you look at it at the top, you'll see again the same issue through a 30-minute runoff event where you have lots of phosphorus running off into the surface waters. So the comprehensive story here is that you can produce this fertilizer at a wastewater plant as part of a solution to address point source challenges, but at the same time, applied in the local watershed, you can address the non-point source challenges. And there's a nice synergy connecting those two things. So to look at this, we completed a third-party LCA life cycle analysis recently, looking at a couple of different geographies, a couple of different crops, and what were the impacts on the environment. And so the three kind of key parameters that were looked at in this LCA analysis were global warming potential, which is essentially carbon footprint. And what you essentially see is that the fertilizer utilization in combination with the benefits of the treatment plant run somewhere between, say, 10 and 15% of reduction in carbon footprint, global warming potential. But the really big impact is on the eutrophication. And so you can see, 50% looks like the highest end, but ironically, if you look at it, corn in Illinois, it says NA, and the reason it's NA is that it's the mathematically you can't look at a elimination of impact. So if you look at an LCA analysis, it looks at impact being generally viewed as negative. In this particular case, say potatoes in Minnesota, it's a 50% reduction in impact. So that's a good step in the right direction, but it doesn't eliminate the impact. If you look at corn in the trial or the analysis for Illinois, it actually becomes a net positive. And what that essentially means is that you can eliminate the impact of phosphate in that application. And then similarly, we mine phosphate rock on a daily basis to manage our food supply. And again, the same benefit in terms of reduced impact for phosphate rock extraction. By collecting phosphorus out of our existing wastewater streams, we can then reduce the amount of fertilizer we have to mine. Now, this is all based on either increasing or at least meeting our current crop production. So doing all of these things is kind of brought back to a net balance, and this is based on analysis per kilogram of crop produced. So similarly, a couple of years back, the US EPA did an analysis around emergy. And emergy is not a common term, I would say, but it's essentially the embedded energy that goes into producing fertilizer. So as a planet, we have a single source of energy, and that is the sun. And ultimately that trickles down into all these other even wind, and you have wind, solar, fossil fuels. They all come from the sun from an energy standpoint. And so this analysis looks at the energy impacts of producing crystal green fertilizer at a wastewater plant in comparison to the energy impacts of manufactured DAP, which comes from mined phosphate rock. And it's a 90% reduction in energy for per unit of fertilizer produced. So at the end of the day, you look at these environmental impacts, and while all of the existing water utilities implement these technologies to meet their permit requirements, which is ultimately their responsibility, there's a great story at the back end around all of the other positive environmental impacts they can have through implementation of the technology and then use of the fertilizer in the local watersheds. Casey, back to you.
Yep, thanks, Matt. All right, so just to summarize, and actually as I was glancing through some of the questions, I think this closing slide may help to start some answers to those questions. But as you're looking at where this technology fits, what's kind of the ideal fit for nutrient recovery with the Wasp Strip and Pearl system? It would be plants, as we looked at, with anaerobic digestion. That's, anaerobic digestion's got the conditions to with the ammonia that's produced there, along with the phosphorus and magnesium that's coming there as well. We like to take the other two out ahead, as we described. And then the other big thing is, as we first started looking at the flow diagrams, you need plants with phosphorus limits that are having to deal with this or expecting future phosphorus limits. And in addition to that, as more and more plants move over to BioP, that's also a good fit with this. If you're taking it out chemically with metal salts and incurring those costs and extra sludge production, you're not going to get those releases we need to form the struvite. We've got to get that phosphorus released. And so BioP is a good way to reduce those chemical costs on the mainstream. And then on the side stream, rather than add metal salts back in to take it out, as we looked at today, let's go ahead with the release, get the phosphorus, magnesium, ammonia over to the Pearl where you can recover a product with it. So plants with BioP over ChemP are preferred for this as well. And then also, as you've got plants out there and running and you're dealing with struvite issues right now, that's a clear sign that this is something that might be a good solution for your problems there. So with that, we'll go to maybe the last slide there. And if, as you guys have questions, feel free to reach out to me with any questions or things I can help with. My contact information's on the last slide. And with that, I'll open it up to the questions.
Great. Casey and Matt, we do have several questions. If we are not able to get to your question today, I will provide a transcript of your questions to Casey and Matt, and they can reach out to you at a later time to answer those questions for you. So I'm going to go ahead and go through the questions in the order that they were received. So, Casey, just for you, back about around slide 20, you had the question, would this system work with a WWTP that doesn't generate sludge and biosolids? The scalping WWTP discharges all solids back into the interceptor sewer line. Hence, solids digestion is not a process at the WWTP.
Yeah, okay. I'll take that question. You can add to it if you've got anything, Matt. But I would say in general, that's probably not going to be a cost-effective solution for this system. And the reason is you really you're not, by not digesting it, you're not getting that ammonia back into the water. You're likely not high enough in phosphorus concentration to really drive the reaction for the pearl. So that probably isn't going to be the best fit for the Astera system in that case. I don't know if you've seen different, Matt.
No, that's 100% accurate. Actually, what ends up happening in those cases is that the centralized location where all of the sludges are then aggregated. This is a very common configuration for Netherlands and some other locations where they essentially set themselves up with processing centers where they manage all the sludges in a central location. The challenge with those central location sites is they're getting all the nutrient loads and they're expected to deal with the recycle coming out of those, centralized digesters, but they don't have the carbon, the alkalinity, and all of the other things and the raw influent that they need to manage those recycles. So it increases the need for management of those recycle loads with a solution such as we've been talking about at the central location, but not at the satellite scalping plants where there really isn't a stream to treat.
And then there was a question that was directly after that. Does this system only work if you have an anaerobic digester?
And I think similar, that is the preferred arrangement because of the ammonia that's generated in the anaerobic digester. A lot of times in systems with aerobic digestion, that ammonia gets nitrified again as you're going through the digestion. I don't know that, have you looked at it, Matt, in the past on any aerobic digestion systems?
Yeah, I mean, quite often you see phosphorus availability, but no ammonia formation.
Yeah.
Um, but that being said, there could be other scenarios such as ATADs and other things that are not traditional anaerobic digestion facilities, or even on the industrial side, UASBs and other, maybe not high solids digesters, but you do see ammonia formation. So there are a few configurations, but generally speaking, in the municipal space, you're going to need an anaerobic digester or an ATAD, something that actually breaks down the solids.
Okay, great. Is the Pearl FX system similar to the former multi-form harvest system that generates a rough end product as compared to crystal green?
The short story is yes. Yeah. So sorry, Casey, but a few years ago, Astera actually acquired multi-form harvest, and then integrating that multi-form harvest reactor technology into the product line, it became the Pearl FX.
Yep, I was going to kick that over to you anyways.
Okay, no worries.
All right.
All right, so is the Astera Pearl reactor performance reduced with high solids content, leading to its location of side stream treatment after dewatering? If so, are there issues with no solids separation with the WASSTRIP unit, or does it treat the decant from the WASSTRIP? Does the WASSTRIP scalp carbon needed for VSR in the anaerobic digesters? And just let me know if you need me to reread any of that.
I'm looking at it, but you want to take that one, Matt?
Sure. So essentially, yeah, we are going to work on the liquors coming off of the solid separation process. So the Wasp Strip tank is typically set up front ahead of the pre-thickening or pre-dewatering going into the digester. So when it hits that thickening dewatering, it will send the solids of the digester and then the liquid to the pearl system. And then similarly on the downstream side of the digester, the solids dewatering cake will go off to either dryers or direct hauling, and then the liquid will come back to us. The pearl reactor is relatively tolerant of solids, but it will work on the liquors, not on the sludge line itself. And then on the carbon comment, the Wasp Strip, there are several different configurations for the Wasp Strip tank. Depending on how it's set up, there are some that use fermentate or primary sludge. It's a relatively small proportion for carbon availability just to facilitate the release of P in the Wasp Strip tank. But it can also be done endogenous, where it essentially ferments on its own and creates its own VFAs for that release. So we've not seen a negative impact, and especially on solids, on digester performance for VSR and gas production. It's hard to track, but in theory it should increase. And then because you're removing the phosphorus chemically without consuming carbon, it actually increases the ratio of carbon to P for the bio-P process, as the recycle comes back around to the front. So it's a net carbon positive process in that context.
All right, great. So we have another question. We have a Class A biosolid that's very desirable to a local farmer. If we utilize this system, will our biosolids still have a desirable amount of plant available phos to appease our farmer?
You want that, Casey, or you want me?
Go ahead. That's more, I think, goes into the fertilizer and.
Well, yeah, I mean, so essentially the short story is that biosolids are P rich, period. So if you apply the biosolids on an agronomic rate, balancing nitrogen and phosphorus, even if we're removing phosphorus from the facility, you're going to have an excess of phosphorus relative to the nitrogen content of those biosolids. So if the site is in any way restricted on P content, and there have been, discussions around phosphorus indexing and the potential implications on biosolids application, if those indexes are present, you're going to be over applying P and therefore need more land to manage on the biosolids side. If you're applying based on P content, then you're essentially nitrogen deficient. So the short story is that it's not going to diminish the value of your biosolids, and it could in some ways improve those operations in terms of reducing the amount of land you need and or the value of it, because the fertilizer is no longer the farmers no longer have the supplement with additional nitrogen to match the P content.
All right. Looks like we've got one last question. If your plant flows are under 5 mgd, is the FX system still viable?
So I guess that comes down to it. If it's got the anaerobic digestion, the phosphorus limits, and all that, it could be. It's something I wouldn't rule out. Something just because of the flow. That's a rough range. I mentioned as far as the 5 to 30 mgd on that, and it's we go down to I think as low as a 6-foot diameter reactor on those FX. So it would be worth taking a look at.
Yeah, and the Paso Robles facility is a 3 mgd plant, just for
Yep,
context.
there you go.
So
Yep.
Okay, looks like we got one that just came in. What's the working range of the solid percentage of those liquors going into the pearl and Wasp Strip? Also, for the additive going into the pearl, Mg and pH leveling, what's the pH range?
You want to take that one, Matt?
Yeah, sure. So on the solids, generally speaking, we're going to see an average TSS content of say below 1,000. What I would say is that none of our existing sites have any solids removal between the dewatering thickening and our reactor. So we take essentially the liquor as it comes to us. That is an average that we'd like to see of 1,000. So they quite commonly see spikes significantly higher than that as centrate storage tanks drain down, for example, and the floatable solids at the top can come to the reactor, or from the bottom of the tank as solids settle out in those storage tanks. So it's relatively flexible, but 1,000-ish is our target. The only caveat to that is we do quite commonly see even say twice that average with THP and other systems where it kind of changes the nature of the solids. But again, we have THP systems functioning just fine. From a pH range, the reactors are generally going to operate between 7 and 8. So that'll depend a little bit upon the specific configuration. I would say most of them actually operate between 7.5 and 8, but it's very unusual for us in a municipal application to go over 8.
All right. That is actually all of the questions that we have, and it actually brings us to the end of our presentation today. Casey, Matt, would either of you like to say some parting words before we end today's presentation?
Yeah, I'd just like to thank everybody for joining today. And as you see anything that looks like it might be a fit, happy to answer questions on that. My contact information is there, so look forward to having those discussions. Thanks for joining.
Yep. Thank you.
All right, this was great. And I just want to take this time to thank Casey and Matthew for a great presentation and to thank Evoqua for sponsoring today's event. This actually concludes today's e-showcase. Thank you all for attending. The recording will be available at wetfiresguide.wef.org. We will send all registrants an email tomorrow with that link. And please visit our event calendar to sign up for future webcasts.